Okay, so in this chapter we'll talk about temperature and heat. We'll learn what temperature actually means. Okay. We all know that temperature tells you how hot an object is. Okay. So let's see what that physically means. Okay. So let me start off by showing you an app. What I'll do is so I've filled this container with some gas. Okay. And there is the pressure of the gas, 32 atmospheres. Okay, that's a very large pressure. In the next chapter, we'll see what that actually means. And the temperature is 300 degree Kelvin. Okay. We'll introduce the Kelvin scale in a minute. 300 degree Kelvin is roughly the temperature in this room. Okay. And so now what I'll do is I'll raise the temperature and see what happens. Okay. So I'll warm this gas. So I'll raise the temperature to, let's say, okay, so I almost doubled the temperature. What did you notice? They're moving faster. Okay? The gas molecules are moving in a random direction. Okay, temperature is a measure of average kinetic energy of these molecules. Okay, so you double the temperature, the average kinetic energy doubles. Okay, that's what temperature measures. All right. So what about in a solid? So this was a gas. Okay, so now let's come to a solid. So here's the model for a solid. Okay, in a solid, the atoms are fixed. They're bound to other neighboring atoms by forces. Okay, so when I heat a solid, so for instance, let's say I heat a table, what happens then? What do you think happens then? Yep.
Well, it depends on how hot you heat it, but I mean, we just heat it by a little bit. I mean, it'll get a little warmer, which means the molecules on where you heat it got a little bit more energy in them.
So yeah. So what happens is they can't move away from their location, but they're vibrating in place. Okay, their energy increases that way.
Okay. If you heat it enough, it'll turn into a.
You're right. We won't. Yeah.
But that's only if you heat it lots.
Yeah. So we're not getting there. So that's what temperature measures: the average kinetic energy per molecule. So here's an amazing fact. So you know that these gas molecules are moving about quite fast. Okay, in this room. The temperature of this table and the temperature of this gas is the same. So what you've learned is the average kinetic energy of these gas molecules and the average kinetic energy of the atoms on the table is the same. Okay? So that's what that means. Okay? All right, so temperature is a measure of how hot an object is. It is a measure of the average internal random kinetic energy per particle of the system. Okay, that's a mouthful. I'll just illustrate one word for you guys. It says average internal random kinetic energy. Okay, what does that mean? Okay, so you know the temperature of this eraser. Okay? The temperature tells you the random kinetic energy. Now, if I move this eraser like this, did its temperature change? So the external kinetic energy does not affect the internal kinetic energy. Okay? So that's what that means. Okay? So it's a measure of the average internal random kinetic energy per particle. The temperature of an object is a number, so it's a scalar that uniquely determines whether thermal energy flows into or out of the object. Okay, so what that means, what that statement means is, let's say this is 100 degrees Celsius, and you bring something in contact at 90 degrees Celsius. Okay, so these are the two temperatures of the two objects. Soon as you know that this temperature is higher than this temperature, that means heat can flow from here to there. Okay, Q is the symbol used for heat. Okay, so when when the object of one temperature is higher than the temperature of the other object, heat can flow from here, one object to another. Okay. How about now? The temperature is the same. Now there won't be any net flow of heat. Heat is still being exchanged, but there is no net flow of heat. Okay. All right. So the temperature heat is conducted from higher temperature objects to lower temperature objects. Okay. So for instance, in this thing, so let's say this could be this table that we're talking about, and in the solid an atom is fixed. If this end is hotter, that means these guys have higher kinetic energy than these guys. Okay, and we'll see how heat is conducted from a hotter end to the colder end later on. Okay. This is just an interesting fact. The new universe started in a Big Bang 13.8 billion years ago. Okay. And the temperature back then was roughly estimated to be 10 to the 39 Kelvin. Okay. Today we are bathed in a background radiation whose temperature is 2.7 Kelvin. Again, just an interesting fact. Okay, thermal contact. Okay, two objects are in thermal contact if they can exchange heat energy. Okay. All right, what is this cup in thermal contact with? I'm sorry? The table, is it in thermal contact with anything else? I'm sorry?
Coffee cup?
Yeah, no, that's what I'm asking. Is the coffee cup in, our friend there said the coffee cup is in thermal contact with the table. Is it in thermal contact with anything else? Yep.
The air,
The air,
if you touch it, they're in
Yeah.
thermal contact with you as well.
yep. Okay. And is it in thermal contact with anything else?
The liquid that's in the cup?
Yeah. I mean, the whole thing. Okay, it's in thermal contact with everything. It can exchange energy with the walls. How can it exchange energy with the walls? So it can exchange energy with the walls via electromagnetic radiation. Okay? It's in thermal contact with everything. You are in thermal contact with everything in this room. Okay? It's just that this contact is stronger than the contact with air and the contact with the walls. Okay? So thermal contact just means as long as you can exchange heat energy with any object, you're in thermal contact with that object. Okay, the strength of the contact might be different. Okay, so two objects are in thermal contact with each other if energy can be exchanged. Okay, energy can be exchanged via conduction. Okay, so this is exchanging energy via conduction. Convection, air gets in contact with this, it warms up. This is a warm cup of coffee. When the air warms up, it expands and it rises up. It leaves behind a vacuum. What happens? Then more cold air comes and gets in contact with that. Okay, and then that warms up and moves away. Okay, that's convective heat transfer. Okay, when a fluid moves, and then you can exchange energy via electromagnetic radiation. Every object emits electromagnetic radiation, and so it's exchanging energy with the walls that way. Did you guys understand that? There you go. Yep. Thermal equilibrium. Two objects are in thermal equilibrium when they have the same temperature. Okay. And when they're in thermal equilibrium, are they exchanging energy? So, for instance, this object and that object are at the same temperature. Are they exchanging energy? They are exchanging heat, but there is no net exchange of heat. Okay? So whenever they're in thermal contact, they can exchange heat. This guy's giving him $1, that guy's giving him back $1. There's no net exchange of money. Okay? So that's thermal equilibrium. two bodies in thermal equilibrium have the same temperature. All right. All right, here is, I'll tell you what this is. Okay, can you come up here? Yeah, sure. Touch this and touch that. Tell me which one is colder or warmer.
This is colder, this is warmer.
So this is colder, this is warmer. They're at the same temperature. She's not a good thermometer. Do it again. They're at the exact same temperature.
No, but it's
It
colder.
is, it is. So what's going on here? I mean, she swears that this is colder. Anybody else? Go ahead.
It's taking your heat.
All right, so it turns out that humans are not good thermometers. What we are sensitive to is, when you touch this metal, it's a better conductor, you're losing heat faster. Okay? So that's what we're sensitive to. When you touch this piece of wood, you're not losing, heat is not being conducted away as fast. Okay? They're exactly at the same temperature. Every inanimate object in this room is at the same temperature. Okay? We are, of course, warmer because we're warm-blooded animals. Well, this room is at a colder temperature than us. Okay, so that's what this says. Okay, humans, to a large degree, are sensitive to energy fluxes rather than temperature, meaning how fast you're losing heat or gaining heat. That's what you're sensitive to. Okay, so humans are not good thermometers. Okay? So, for instance, fluxes rather than temperature, which you can verify for yourself on a cold, dark morning in the outhouse of a mountain cabin equipped with wooden and metal toilet seats. Yeah. Both seats are at the same temperature, but your backside, which is not a very good thermometer, is nevertheless very effective at telling you which is which. Yeah. So again, we are sensitive to heat flow in and out. Okay? We're not good thermometers. All right, now we've defined temperature. Temperature is the average, is a measure of the average internal kinetic energy. Okay, so again, going to this thing, temperature tells you what is the average kinetic energy of these molecules. Okay. You double the temperature of this gas, you double the kinetic energy of these molecules. Okay. All right, so now let's look at how do you measure temperature of an object. Okay? So we'll talk about various temperature scales. Now it turns out that in the physical world, phenomena happen at the same temperature. For instance, at 1 atmosphere, if you freeze water, you can freeze it today, you can freeze it tomorrow, you can freeze it in the morning, you can freeze it at night. It always freezes at the same temperature. Okay? And if you boil water, for instance, at 1 atmosphere, you can boil it in Florida, in New York, as long as the atmosphere is 1 atmosphere. You can boil it in the morning and stuff like that. It always boils at the same temperature. Okay? So now if you want to invent a temperature scale, you call this freezing point of water one temperature, and the boiling point of water another temperature. Yeah. So how many scales can you invent? I'm sorry? Okay, so to get the temperature scale, you call this freezing point of water one temperature, and the boiling point of water another temperature. So on the Celsius scale, they call this 0 degrees Celsius. They call that 100 degrees Celsius. On the Fahrenheit scale, they call the freezing point of water 32 degrees Fahrenheit, the boiling point of water 212 degrees Fahrenheit. Okay? We'll come to the Kelvin scale. Okay, so the Kelvin scale, they call this 273 degree Kelvin, and this 373 degree Kelvin. Okay. How many scales can you invent? I'm sorry? Infinite, as many as you want. You can call this anything you want, and that anything you want. Okay? Now, since this is warmer, you want to call that a higher number. Okay? So, but these are the three scales that are commonly used. Okay? So let's look at, yeah?
Just had a random question.
Uh-huh.
I never really thought this before, but I forget, what exactly is the 0 degrees in Fahrenheit based on? Like, what did they use to tell 0 back in the day when they made the Fahrenheit scale?
So we'll come to that in a second.
Oh,
I'll
okay.
answer that with the Celsius scale. Okay?
I
And
know
we,
Celsius and Kelvin, but I never knew Fahrenheit.
okay. Well, yeah, I don't know the story on that one either, but I know the story on this one. Okay. All right. So let's see. One of the things is, okay, so between these two temperatures, there's 100 degrees. How many degrees are there between these two temperatures? 100. Okay, so this seems like these two scales are similar. And why have these two scales? And we'll come to that. Okay, how about this guy? Between these two guys, there's 180 degrees. So this is a finer scale. Okay, so it's a finer grain. So each degree here is about half a degree here. Okay, so this is a finer scale. All right. So again, to make a scale, all you need is you need two physical phenomena that happen at the same temperature, and commonly used as freezing point of water and boiling point of water. Okay. All right. What these formulae do is they let you, so if you have a temperature in a Celsius scale, you can convert it into Fahrenheit scale like that using this formula. So let me do an example. So let's say if you have 20 degrees Celsius, you want to know what is it in Fahrenheit scales, on the Fahrenheit scale. So what you do is 9/5 times 20 plus 32. Okay, that's 4. 20 divided by 5 is 4. 4 times 9 is 36. 36 plus 32 is 68 degrees. Okay? So that's how you would do that. Okay? Now, you can, so you can accurately calculate it, but if you want to do it fast in your head, see, 9/5 is essentially roughly 2, close to 2. So if you have 20 degrees Celsius, multiply that by 2. Okay, 2 times 20 is 40. 40 plus 30 is 70, roughly 70 degrees. Okay, so that's a quick way of doing it. All right, if you wanted to convert from, so if you wanted to get Fahrenheit to Celsius, TF minus, so this is how, all I've done is rearrange the terms. Bring that to the other side, so TF minus 32, and then cross multiply 5 nines, okay? So if you have a temperature in the Fahrenheit scale, this is how you get the Celsius scale, okay? So if you have a temperature on the Celsius scale, let's say 70, okay, we'll do 72. 72 minus 32 is 40. 40 divided by, this is roughly 1/2. 40 divided by 1/2, times 1/2 is 20 degrees. Okay. All right. So this formula allows you to convert from Fahrenheit to Celsius or Celsius to Fahrenheit, and this formula allows you to calculate from Celsius to Kelvin scale. Okay. So if you have a temperature in the Celsius scale, 27 degrees on the Celsius scale, 27 plus 273 is 300 degree Kelvin. Okay. So between these formulas, you can convert the temperature from one scale to another. Okay, so all right. Now we'll talk about absolute zero. Okay. All right, so let's come back to this this app. You can see that temperature measures the average kinetic energy of these molecules. Okay, and I warm the gas up, the gas molecules move faster. Okay. Now let's do the opposite. Let me cool down the gas. As I cool down the gas, the temperature falls and the gas molecules are getting slower. Okay, if I cool down further, what will happen? The gas molecules will slow down further. What is the best I can do? Yep. Stop them. Okay. And then after that, I can't cool them anymore. So when all molecular motion has ceased, that's the lowest temperature you can possibly get. And that's called absolute zero. Okay? So when we realize this, okay, so let's go back to this scale. Okay, so go to the Celsius scale. When you cool down the gas and all molecular motion has ceased, the temperature you get is minus 273 degrees Celsius. Okay? That is the coldest temperature you can reach. Okay? Now, that's a very odd number. You tell your little brother that minus 273 degrees Celsius is the coldest temperature you can reach. That's why minus 273. Okay? That's just an odd temperature. So this Kelvin scale is just a rescaling of that. We call this 0 degree Kelvin. That's absolute zero. Okay? So that's just a new scale. And the Kelvin scale is the same as Celsius scale, except that the zero is recalibrated. And so this is 273 degree Kelvin, this is 373 degree Kelvin. Okay. All right. So what this graph shows you is you can take, so this is how the absolute zero was discovered. You can take three different amounts of gases in a flask, or okay. So you take a flask, fill it with so much gas, and in another flask, same flask, fill it with more gas, so the pressure is higher. Okay, they're all at the same temperature, and more gas and the pressure is higher. And as you cool these gases, the pressure all goes to zero at the same time. And the pressure goes to zero. See, the pressure is because these gas molecules are bouncing off the walls, and when they come to rest, they're not bouncing off the walls anymore, and the pressure has gone to zero. Okay? And that's how absolute zero was discovered. Okay? So as you cool down the gas, the pressure is going to zero at the same point. That is when all molecular motion has ceased, pressure has gone to zero. Okay? So at absolute zero, all molecular motion ceases and internal energy of the system is zero. All right, so now that we have talked about temperature, again, temperature measures the internal random kinetic energy per particle. Okay, so now let's look at some of the temperatures we have measured. Okay, okay, here's the temperature of a hydrogen bomb explosion. Okay, so here's a bomb that is exploded, and the temperature at the center of the explosion is 10 to the 8 Kelvin, or 100 million Kelvin. Okay. This is the temperature at the center of the sun. So this is this was the bomb exploding. At the center of the sun, the temperature is 15.6 times 15 million degree Kelvin. Okay. All right, so here's an important thing we need to understand. Okay, so let's say the bomb exploded here, and we are saying that the temperature at the center of the explosion was 100 million degree Kelvin. How do we know that? Did somebody put their fingers at the center of the explosion? Okay, so we want to know how do they measure that temperature. Solar corona, so this is the temperature at the center of the sun, 100 million degree Kelvin. The solar corona is the sun's atmosphere. The temperature here is a million degree Kelvin. Okay, so here's how we measure the temperature of a remote object. Okay. So okay. Now, if you take a solid or a liquid and heat it up, well, every object emits electromagnetic radiation. And what this graph tells you is the following. So, okay, this is the intensity of the radiation, and this is the wavelength of the radiation. The wavelength is related to color. See, different colors of light have different wavelengths. This is infrared. This is infrared wavelengths. These are UV wavelengths. Okay, and these are visible light. And now, so if a body is at a given temperature, this is the curve it emits. Okay, it emits this wavelength, it emits that intensity, this wavelength, that intensity, and so on. So for every wavelength, it's a different intensity. Okay. Now let me change the temperature of this this object. Okay. So that's the temperature of the sun. Okay. And that's the radiation coming to us from the sun. That's the surface temperature of the sun. Okay. Now let's change the temperature. So here's a different star. Okay. I changed the temperature and the curve changed. Okay. So for every temperature, the curve is unique. Okay. So if you want to measure the temperature of some object, so I want to measure her temperature, what I do is I'll measure the intensity of different radiation coming from her. Okay. I measure intensity for this radiation, intensity for this radiation, intensity for this radiation, and I know exactly what curve fits that. Did you guys understand that? Okay. And I know the temperature. And then I'll know the temperature. And that's how those thermometers work. The no-touch thermometers, that's what they're doing. Okay? All right. So you want to measure the temperature of any object, remote object, that's how you do it. Okay? So that's how we know the temperature of the atmospheres of various planets. That's how we know the surface temperatures of various stars and so on. Okay? Nobody sticks a thermometer in a furnace. Okay? So you're measuring the radiation coming, the intensity of radiation coming from the furnace, and that's how you know the temperature. Okay? So you see you have to measure intensities of 4 or 5 different wavelengths, okay, and fit the curve. Okay. So now you know how the no-touch thermometer works. Okay. All right, now let's say we heat this table. Okay, so here is a model of a solid. Okay, I'm going to add heat to it, heat to the solid. What will happen when I heat this solid? When I heat the, I'm sorry? It expands. Very good. Okay, so here's one of the things we do. These molecules move faster since the temperature rose. And also, these atoms go further apart. Okay, so the kinetic energy increases and the potential energy increases as well. Okay, so the average kinetic energy increases and the average distance between the molecules increase. Okay, so since every molecule is going further apart, the solid will expand. Okay, so when you raise the temperature of a solid, it expands. Okay.
If it isn't the spring that brings it back, can't go too far?
Yes, so depending on how much energy you put in, so it's like, all right, you've seen a spring, I put in energy, I can expand it. Okay. More energy I put in, more I expanded it. Okay, you put in the energy, but when it contracts, it will give the energy back. But if you're maintaining that temperature, it'll remain expanded.
Like a rubber band?
Like a rubber band. Okay. Okay. So, when you raise the temperature of a solid, because every molecule or every atom is further apart, the solid will expand. Okay. Now it'll expand in all directions, but if the largest dimension is the length, the most noticeable change will be in the length. Okay. So let's say this object expanded. The increase in length is equal to the original length times the rise in temperature times a number that depends on the material. Okay? So different materials will expand different amounts. Okay? So for instance, an aluminum ruler would expand more than a wooden ruler with change in temperature. Okay? Alpha is the coefficient of linear expansion. Okay? So that's the name given to it. Okay? So here are some numbers. Again, these numbers are important enough that you have these tables. So for instance, for aluminum, the coefficient of linear expansion for aluminum is that 25 times 10 to the minus 6, okay, per degree Celsius. Okay, so let's see what that means. So let's say you have a aluminum meter stick. Where's a meter stick? Okay, so a meter stick is about this long. Okay, what we're going to do is we're going to heat this by 1 degree Celsius. Okay, so here's a 1 meter aluminum meter stick, and we're going to, so 20 degrees Celsius, and we are going to raise the temperature to 21 degrees Celsius and measure the expansion. Okay, so the expansion is given by L times change in times alpha. Remember, this was 1 meter, so that's 1 meter. We're going to raise the temperature by 1 degree Celsius, and alpha is 25 times 10 to the minus 6, okay, per degree Celsius. So 25 times 10 to the minus 6 meters is the expansion. Okay, so, and okay, again, you don't have to remember all of this. 10 to the minus 3 millimeters. 10 to the minus 3 meters is a millimeter. Okay, so 0.025 millimeter. Okay, 1 meter of aluminum will expand by 2/100ths of a millimeter. That's a very tiny expansion. This is 2/100ths of a millimeter. Okay, so 1 meter of aluminum would expand by 2/100ths of a millimeter if you raise the temperature by 1 degree Celsius. Okay? So these expansions of solids are very tiny, but they're important enough where they're given you a table. So how does it affect our lives? Okay, so here's an example. And you've seen this all. So here's a bridge in Michigan. Okay, it's a kilometer long, 1,158 meters. Okay, a kilometer is roughly from here to the Embry-Riddle campus. Okay, so the bridge is that big. Okay, between the dead of winter and in the peak of the summer, it sees 100-degree change in temperature. From the coldest to the hottest, it sees 100 degrees Celsius. Okay, so you can do the numbers on this. L, you can put the length of the bridge, change in temperature would be 100, and alpha. Okay, and so this bridge that goes from here to Embry-Riddle would expand 1.5 meters. Okay, this would work out to 1.5 meters. 1.5 meters is your height. So that's how much the bridge would expand. Okay. Now you got to accommodate for that expansion. And between every span, they'll leave a gap like this. Okay. So when in the summer the bridge warms up, see these gaps close. You've left these gaps in the bridge expansion of the bridge. Okay. If you've walked across any of these bridges here that we have, every bridge has these expansion gaps. Okay. And if you didn't have these gaps, if the bridge was one solid piece of metal, it would expand and buckle and it would crumble. Okay. So you have to leave these expansion gaps. We do that on our train tracks as well. So on train tracks, so here's one rail, here's the next rail, okay, and there's this expansion gap for when it warms up, okay. And if this expansion gap is not big enough, this is what happens, okay. This track pushes against that and they'll bend, and a train going on that will derail. Okay. So you guys understand that? So even though the expansion is small, you have to leave these expansion gaps. There's another place that you see this in everyday life. Can you think of any other place where these expansion gaps are there? When you walk on the sidewalk, you see that cut, that's an expansion gap. Okay. All right. Here's another example. So for the trains, here's an amazing number. The Trans-Siberian line runs 9,300 kilometers. That's So this is a train track that goes from St. Petersburg to the eastern, it goes to Vladivostok, so, and that's about 10,000 kilometers. That's going from here to San Francisco and back, okay? And all those gaps, so it sees a temperature change of about 60 degrees, and those gaps add up to 8 kilometers. All those gaps would add up to from here to Ormond Beach. Okay. So that's how much the expansion gap is. Okay. All right, now let's talk about heat. This is a term that you hear all the time. Okay. All right, so let's say we have two solids, and this is at 60 degrees Celsius, and that's at 50 degrees Celsius. When you bring them in contact, what will happen? What will happen? Heat will flow from here to there. Okay, heat flows from the hotter object to a colder object. So what is happening at the microscopic level? So here is a model of this solid. When it's at 60 degrees Celsius, these atoms are vibrating with a larger amplitude. These guys, so that's so this is 60 degrees. These guys are vibrating with a larger amplitude. They have more energy than these guys. Okay, and what happens is some of these guys give some of their energy there, and their vibration decreases, and their vibrational energy increases. Okay, how long will the heat flow? How long does heat flow from here to there? You guys know this answer, yeah?
I mean, basically until they're both in equilibrium.
Till the temperature comes to the same temperature, okay? What that means is when the temperature is the same, the average kinetic energy of each molecule is the same, okay? So heat makes up, so they share some of their kinetic energy, and as the temperature drops, their distance between the molecules is decreasing as well. And so they're sharing some of their potential energy as well, okay? So heat is the sum of these random kinetic energy and potential energy. So heat is the internal energy transferred between objects because the temperature difference between the object. Internal energy or thermal energy of the system is random internal kinetic and potential energies. Kinetic and the potential energy, okay? So that's what you're exchanging. Yep.
Go back, please.
Mm-hmm.
Yeah, I'm almost done.
Yep. All right, so now we'll talk of units of heat. This was the first unit of heat defined, 1 calorie. Hello there. Hello. Can you hold up your bottle, please? Yeah. So, yeah. You take a cap full of that water, that's about a gram of water. A calorie was defined as 1 calorie was, you take that much water, you raise its temperature by 1 degree Celsius, and you've used 1 calorie of heat. Okay? So that's how the calorie was defined. 1 BTU is the heat needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Okay. Now, we don't use this unit, so, but this is in science classes we don't use this. Okay, we use the calorie and the joule. Okay. So joule is the SI unit for energy, and it turns out that 1 calorie is 4.184 joules. Okay. A food calorie is a big calorie, is a 1 kilocalories, 1 is 1,000 calorie, and so food calorie is 1,000 of these calories. Okay. Now, initially, back in the old days, 200, 300 years ago, they thought heat was some kind of fluid in a solid. So when two objects came in contact and they exchanged heat, they thought that some kind of heat fluid flowed from here to there. Once they realized that heat was a form of energy, they had to they needed to see how much a calorie was in joules. Okay, how many joules was a calorie? Okay, so this was the experiment Mr. Joule did, and that's why we have named the unit of energy after Mr. Joule. Okay, so here's what he did. Okay, so you can see that here's a weight hanging by this rope, and as this weight falls, this rope unwinds, it turns this paddle, and when the paddle turns, it warms up the water. Okay, so when this object falls a distance h, it loses this much energy, which can be calculated in joules. Okay, when this paddle turns, the water warms up, and so the amount of heat that went into the water, this is the mass of the water, the specific heat of water, the rise in temperature, and this can be calculated in calories. Okay, so what happened in this experiment is when this guy lost this amount of energy, all that energy went into heating this water. So Mr. Joule could calculate this many joules got converted into this many calories. Okay? And that's how you found this. Okay? So once we realized that heat was not some kind of fluid, it was a form of energy, this experiment had to be done. Okay? And that's why in his honor we named the unit of energy as joule. Okay? So this was a very important experiment. All right, now we'll talk about specific heats. All right, so let's say this is aluminum and this is iron. Okay, and we have a kg of both, or a pound of both. Well, we'll take 1 kg of both. All right, I want to raise the temperature by 1 degree Celsius. Will I need the same amount of heat? What do you think? Different amounts, okay? So the amount of heat needed, okay, so if you have a mass M and you want to raise its temperature by T, so, and then the amount of heat will depend on the material you're heating. And this thing is called the specific heat. Okay? So this is the amount of heat needed to raise the temperature of a solid or a liquid. M is the mass, the amount of stuff you have. Delta T is the temperature by which you raise. And C is the specific heat. Okay? So higher the specific heat, more heat you need to raise the temperature. Okay? And for a given amount of heat, higher the specific heat, less the temperature will rise. Okay? So what we want to remember is higher the specific heat, harder it is to change the temperature of the object. Okay? So higher the specific heat, more heat you'll need to raise the temperature of the object. Okay? So that's what the specific heat tells you. Specific heat is the amount of heat needed to raise the temperature of 1 kg of object by 1 degree Celsius. Okay. So the units will be joules per kg per degree Celsius. Okay. So that'll be the units of that. Okay. Now, when you're dealing with solids and liquids, mass is easy to measure. When you're dealing with gases, the number of moles is easy to measure. So you define specific heat, molar specific heat. I guess I just want to mention that. We won't come to that in a second. Okay. We won't talk much about it. All right. So now we'll talk about the following fact. You guys all know, is waterfront property expensive? Why is waterfront property expensive?
The view,
I'm sorry?
the view,
The view is part of it.
Voting,
I'm sorry?
voting.
boating. Okay, so here's why waterfront property is really expensive. Okay. All right, so let's look at the specific heat. You guys remember, the higher the specific heat for a given amount of heat, the lower the temperature rise. Okay, so higher the specific heat, more heat you would need to raise the temperature. Okay, look at this. The specific heat of water is 4,200 joules per kg per Kelvin. Dirt is silicon dioxide to a large extent. Its specific heat is that, 703. So the specific heat of water is 6 times greater. All right, now let's come to this diagram. Okay, let's say during the day, you have the same amount of heat falling on water and land. Okay. Now, the same amount of heat is falling. The specific heat of water is 6 times greater, so its temperature will rise 6 times less. The temperature of the land will rise 6 times more. Okay, land will get hotter. What will happen? The air here will get warmer, it'll expand, and it'll rise up.
So the temperature of the water will,
The temperature of land rises up more because it has lower specific heat. Okay? So during the day, so here's the ocean, here's land. This gets warmer, the air gets warmer, it expands and it rises.
so is
That's-
water decreasing by 6 times?
I'm sorry?
Is water decreasing if land is increasing?
No, okay, so here's, mass times specific heat times temperature. Okay, you're putting the same amount of heat on both land and water. And since the specific heat of water is much higher, the temperature rise is lower. Okay? If the specific heat is higher, the temperature rise is lower if you put the same amount of heat.
The temperature is the reason why waterfront properties are so expensive?
We'll come to that in a second. The story is not complete yet. Okay? All right, so you guys understand that? During the day, the land is warmer, air expands, it rises up, it's leaving behind low pressure, and so there's high pressure on top of the water, and you have a breeze from the ocean to the land. Right? Everybody understand that? So there'll always be a breeze. Okay. Why is there a breeze? Because the air on the land gets warmer. Okay. And it rose up, left behind a low pressure, and air flowed from a high pressure to low pressure. All right, now let's wait 12 hours. It's become night. Okay. Remember, this water can hold a lot of heat. Okay, so it takes a while for water to cool down. So at night, this didn't have too much heat. Land cooled down faster. So now the temperature of the land is cooler than that of water. Now the opposite is happening. This air expanded, this rose, it left behind a lower pressure, and there's a breeze blowing from land to the ocean. So if you buy a house here, you'll always have a breeze. You buy your house is next to a large body of water, you'll always have a breeze, and the temperature of the body of water doesn't fluctuate as much as the temperature of the land. Okay, you can do this, you can see this anywhere. You get a beachfront property and all you have to do is come 2-3 kilometers inland. 3 kilometers inland, the temperature is higher, 3 to 5 degrees Fahrenheit. Okay. The view is pretty, but the weather is more moderate around a large body of water. And that's what you pay the money for. Okay. All right, did you guys understand that? So how do you have a breeze? The breeze is, so to have a breeze, what you have to have is two regions with different temperatures. The higher temperature, air expands and it'll rise, leaves a lower pressure, and you'll have a breeze from a higher pressure to lower pressure. Okay? And you can do this in you can feel this in a parking lot as well. In a parking lot, and this is grass in a meadow, a parking lot will heat up because of asphalt. This air will get warmer and rise up, and so you'll have a breeze from the meadow to the parking lot. All right, so now we've learned how breezes happen. Okay. So this is an extremely important number. The specific heat of water is, like I said, 6 times greater than that of land. Okay. The specific heat of water is a very important number that plays in our lives. Okay. All right, now I'll tell you a story that's sort of relevant to life. Okay. The density of a material denoted by rho, the letter rho, Greek letter rho, is the mass of the object. The density of a material is the mass of an object divided by volume. Okay, so here the density of the material is mass divided by volume. Now let's say I heat this material. What will happen to the volume? If I raise the temperature of the object, if I heat it, the temperature rises. What will happen to the volume? If you heat something, what happens to the volume? It expands, right? I mean, everything expands. So you heat it, it expands. So if you raise the temperature, if the volume increases, the density decreases. Yep. That's what happens for most materials. Okay, look at this. This is density of fresh water. In this small window, 0 to 4 degrees, you're raising the temperature. You're raising the temperature. The density should decrease. But for water, the density is increasing. And only in that small window. And after 4 degrees Celsius, like every material, as you increase the temperature, the density decreases. Now, this little bump is extremely important. Okay? And we'll look at that. Do you guys understand this? So, in this small window, the density has increased. And this effect is, you see, it's about 10 in 10,000. It's a very small effect. Okay. But we'll see why this is important for life. Okay. And in addition, when you freeze water, ice is less dense and it floats in water. We all know ice floats in water. Okay. So now let's do the following. Yep. Let's say you have a lake and you want to freeze the lake. How do you freeze a lake?
From warm,
Hmm?
from the warm air.
No, let's say there's a lake in your backyard, you want to freeze it. How would you freeze a lake? So here's how you do it. You go and flip a switch and turn the temperature of the air cold. Okay? Well, what will happen? So let's say this lake was at 10 degrees Celsius. What will happen? Heat starts flowing like that. Okay? And let's say then this comes to 4 degrees Celsius. All right, let's go back to our graph. At 4 degrees Celsius, the density of water is highest. Okay. Now, be patient with the story. It's a good story. Make sure you understand it. At 4 degrees, the water is densest. Okay. So this 4 degree water, since it's densest, it'll go to the bottom. You guys understanding that? So that'll be 4 degrees Celsius. And then there's more water, and eventually all of the water will get to 4 degrees Celsius. Every layer is 4 degrees Celsius.
That's still warmer.
Yeah, we're getting there. We haven't frozen the lake yet. We got to freeze the lake. All right. does this air is still at minus 20 degrees. Heat will still flow. Okay, now, so this guy goes to 2 degrees Celsius. Now, if water was like any other substance, this would have been denser and that would have sunk. But see, our graph tells at 2 degrees Celsius, the density is lower. This water is not going to sink. All right, more heat flows, and this guy falls to 0 degrees Celsius. And that's still less dense, it won't sink. That's very important. Now more heat will flow, and this guy freezes. And a sheet of ice is now a nice blanket. Now it'll cut off the heat flow. Okay. And now you can't freeze this lake anymore. So did you guys understand that? So you try to freeze a lake, all you end up doing is freezing the top layer. And then this thing, the bottom layers are all at 4 degrees Celsius, but it'll remain water. And now, fish can swim in this. They can survive the winter here. Had the whole lake frozen, life couldn't have survived through the winter months. Yeah. So that little bump is extremely important. Okay? Yep.
So you say the other substances are like that. I've always heard of this
Mhm.
phenomenon with water.
Uh-huh.
What I always wondered is why does water act that way? Like what property does it have that makes it expand instead of getting denser at that certain temperature like the other materials?
It's got to do with packing. So when material is denser, then you're packing the molecules closer. And
Yeah.
so whatever the intermolecular forces are.
Okay, so just due to how the molecules are, when it gets to that cold thing, the packing,
Mhm.
it doesn't stay, yeah, basically just the structure of other things that makes it less dense, but it's still getting colder.
Yeah.
Okay, that makes sense.
And also, so for instance, also then the bigger, so same argument goes, when you freeze water, so at when you freeze water, you're lowering its temperature, but the solid ice expands, its volume is 10 times greater. Again, it's a packing issue.
Are there many other materials that do that, like methane?
No, not many materials do this. So
Okay.
water is
Some
unique.
people, some people ask us, say, for example, Titan has like lakes of liquid methane. It'd
Mhm.
be interesting if it had a similar effect if there was, some extremophile version of life there that could function at the same
Yep.
thing, just with methane instead of water.
That's the thing about science. There's so many interesting things. So I told you a beautiful story about this little bump. And that's 10 parts in 10,000. Okay? So that's why we talk about these little things. Yep. I mean, you might miss this if you... All right, so again, so little things make up a lot of stuff. All right, we'll do one more...
I have a question.
Okay.
So going back to the lake.
Mm-hmm.
So
You
no
still
matter-
want to freeze the lake.
So no matter what the temperature, how cold it freezes on top,
Mm-hmm.
it will never freeze through?
Yep.
Okay.
Mhm. So now that we are about freezing lakes and stuff like that, let's talk about, let me give you another great number. Okay.
Well, actually,
Okay, just a second.
yeah, I'm sorry.
So here are the 5 big lakes up north. You guys. And during the winter, they freeze, and so so just Lake Superior. Okay. Lake Superior is roughly half the size of Florida. Okay. And a layer of ice 1.5 meter thick forms in the winter. 1.5 meters is roughly my height. So cover half of Florida with my height with ice. Okay. To freeze, what needed to happen? Heat needed to flow from here to there. And again, you are an expert in freezing lakes now. All you do is minus 20. All right. You know how much heat you have to remove just to freeze the top layer of Lake Superior? As much as contained in 10 million atom bombs. That's how much heat you have to remove. That's just one lake. And then what do? 3 months later, you're bored and you melt all this ice. So you put back that much heat. Nature moves an enormous amount of heat back and forth. And this is just one piddly little lake, I'm telling you. So there are some amazing numbers out there. Yep.
So I was gonna say two things. One, like if it was cold enough, theoretically you could freeze the entire lake if it was cold enough, but it would have to be.
You'd have to wait a long time because the layer of ice
It'd
is.
take a long time.
Yeah.
And secondly,
Mhm.
it would just have to be ridiculously cold. And secondly, I guess, you make an inference, I guess that's why, things like ice caps melting is such a huge problem, is because not only does it raise the water level, but it's also transferring a bunch of heat back in the atmosphere, I would guess. 'Cause,
No,
they're
I mean-
storing that much heat as they're frozen, right?
You can melt. No, melting something is easier. All you need to do is just bring in more and more heat. That's easy to do.
Yeah.
And that's.
But the water that's frozen, like you're saying, it's storing a crap ton of heat, right? Because it's frozen, and then as it heats back up, it's.
No, when you freeze, you have less energy.
Okay, yeah, sorry.
All right.
Never mind.
All right.
Sorry.
Okay, I got to tell you one more important concept. And this is yeah, and this will be important. See, we are warm-blooded animals, and we maintain a constant body temperature, and that's very important for us. So like I said, you're all glowing like a 100-watt bulb, and so your body is getting rid of 100 joules of energy per second to maintain your body temperature. Okay? So, okay, again, your bodily processes 100 watts means 100 joules per second. You're producing 100 joules of heat per second. So if you don't want your body temperature to rise, you have to get rid of this much heat per second, right? And then you go for a run. Let's say you're producing 1,500 joules per second, and suddenly your body's air conditioning system has to work 15 times harder to maintain that body temperature. Okay, so we'll see how your body does that. Okay, and to get to that, to understand that, so we'll have to understand this concept of latent heat. Okay. So let me do this. And by the way, I'm not going to be able to finish this chapter today. So what will happen is next Tuesday I'll finish the chapter and then we'll do the quiz. Okay, and then I'll start the following. Okay.
Do we still have a test on Monday, or by Monday?
No, you don't.
Oh.
Your test is always after you finish your. Okay. All right. Here's a glass of ice from your freezer. And this ice is at -5 degrees Celsius. That comes from your freezer. Let's heat it. We'll get a pan full of ice and put it on the range. What will happen? What do you think will happen?
It'll melt.
Okay, so it turns on. So that's the standard answer. None of it will melt. What will happen is the temperature will rise, the ice will warm, and it'll get to 0 degrees Celsius. And you still have it on the range. You're still heating it. And what happens now? Now it starts melting, and the temperature won't rise. Okay, so this is heating, this is temperature. So let's say you start at a -5 degrees Celsius. It rose to 0 degrees Celsius. So you're adding heat. And the temperature will remain at 0 degrees Celsius till what point? Till all of the ice is melted. Okay? Once all of the ice is melted, then the temperature of the water will start rising. Okay, all this heat that you added and that didn't raise the temperature of the substance is called latent heat. Did you guys understand that?
Which part is the latent heat?
The part that didn't go into raising the temperature.
Like, is the heat that goes into,
Melting the ice. Okay, so temperature measures this kinetic energy of the molecules. So you added all this heat, the molecules are not getting faster. So where did that heat go? It went into breaking the bonds, okay, of the solid. Okay, so when phase change happens, again, you want to understand this. When phase change happens, so from solid to liquid, or from liquid to gas, okay, you're adding heat, which is called latent heat, which is not raising the temperature. It's breaking those bonds, okay? And so this is called latent heat. Okay, and for latent heat of water, it's 80 calories per gram. And this is called latent heat of fusion for water. Okay, you want to remember this number. What does this number mean? To melt 1 gram of ice, you need 80 calories of heat. And if you wanted to freeze 1 gram of water, you would have to remove 80 calories of heat. Okay? All right, so latent heat during phase change, meaning solid to liquid or liquid to gas, heat added does not raise the temperature of the substance. The latent heat is required to overcome the intermolecular forces. So for instance, here is the solid, and you are adding heat, which is going into breaking these bonds. And when substances melt, you've broken those bonds, and this has become liquid. Okay? So a similar phenomenon happens when, so here is ice. You're adding heat added, the temperature is rising, and once ice starts melting at 0 degrees Celsius, the temperature remains constant, and all the heat added went into breaking these bonds. Okay? And once all the ice is melted, now you can raise the temperature of water. All right, now we're not going to stop there. You got water, and you keep warming the water, and once the water gets to 100 degrees Celsius, now if you add heat, the temperature of water does not rise. All the heat goes into converting the liquid to gas, okay, to water vapor. And once you get to water vapor, all of that has become steam. Now you can raise the temperature of steam all you want. Okay. Okay, this is called the latent heat of vaporization. For water, the latent heat of vaporization is 540 calories per gram. Okay, what that number means is, to convert 1 gram of water to steam, you need 540 calories of heat. So I want you guys to remember those two numbers. Latent heat of fusion is 80 calories per gram, and latent heat of vaporization is 540 calories. That's an enormous number, and it's a very important part of our life. Okay? So latent heat is denoted by L, is the heat that must be added to or removed from a unit mass of substance to convert it from one phase to another. So if you want to melt something, how much heat do you need to add? So if you want to melt m grams of ice, of m kg of ice, it's m times the latent heat. Okay. So the heat of fusion of water is 80 calories per gram. To melt 1 gram of ice, you need 80 calories of heat. Conversely, if you want to freeze 1 gram of water, you have to remove 80 calories of heat. Okay. To vaporize 1 gram of water, you need 540 calories of heat. Okay. These two numbers are extremely important, and will the latent heat of vaporization of water is quite large. It's the energy source for hurricanes and steam burns. Okay, so what this means is, okay, so let's say, now this is a healthcare relevant example. 1 kg is 2.2 pounds. Okay. All right. Here, I'm going to throw 1 kg of hot water at 100 degrees Celsius, or I'm going to spray you with 1 kg of steam at 100 degrees Celsius. I mean, you don't want either one of them happening to you, but which would you rather if you had to choose between one of the two? You want this one?
Well, I didn't hear what the first one was.
The first one is 1 kg of hot water at 100 degrees Celsius, or this is 1 kg of steam sprayed on you at 100 degrees Celsius. They're both at the same temperature.
I'm gonna go with the steam's worse.
Huh?
I'm gonna go with the heat.
Steam is worse. That's the correct answer. Why is the steam worse? Okay, so that's what you just learned, the latent heat of vaporization, 1 kg. So this is, steam has 540 calories per gram more. 1 kg is 1,000 calories. So 1 kg of steam will have 540,000 calories extra. What will happen is when you get this steam, when it condenses to water, it deposits this many calories of heat to your body, and then it's still 100 degrees of water. It has that much extra heat. Okay, so people in the healthcare industry probably know steam burns are bad. They have that extra energy. Okay? All right, so burns produced by condensation of 100 degrees Celsius steam on the skin are more severe than those produced by same mass of 100 degrees Celsius water. This is due to the extra energy released when steam changes state from gas to liquid. Okay, so that latent heat of vaporization, okay, burns a lot. All right, so here are latent heat for various materials. So this is in joules per kg. These numbers are hard to remember. What are easier to remember is latent heat of fusion is when it goes from solid to liquid. Latent heat of vaporization is when it goes from liquid to gas. Okay, so I want you guys to remember for water, this is 80 calories per gram. That's easier to remember. This is 540 calories per gram. Okay, those are important numbers, and this is for alcohol. Okay, and for alcohol, this is about 240 calories per gram or something like that. And we'll talk about alcohol rubs later. Okay. All right, we will stop here.